an IITG person promises only what he can deliver, and an IITG person delivers what he promises.
Hello, today I will be continuing the remaining part of the previous lecture. In previous lecture, we were discussing about the slab base and then the gusset base, the design procedure, and one example of slab base we have given already, and also the design procedure of the gusset base we have discussed, but we couldn't finish the example, workout example. First, today I will do the design steps and some example of grillage foundation. After that, if we have time, then the previous lectures workout example I will complete. So, as per the time permits, we will go one by one. Okay. Here I have write down the salient features, I will just read out, because if I want to tell many things, it will take lot of time. So, just coincidentally I will try to discuss in terms of salient features about the grillage foundation, so that actually in limited time, limited number of lectures, at least we can discuss little more, right. So, today I am going to discuss about the grillage foundation. So, what is grillage foundation, when it is required? Basically, grillage foundation is required when the load from the column is coming very high. When it comes in case of tall building, columns are heavily loaded. So, in that case, if we want to provide the base plate by the method of gusset base or slab base, then what will happen? The area of base plate will be becoming very high, which may not be economic. And another thing is, if the soil is soft in nature, then the area of concrete block will be required again very high, right. So, area will be, that is impractical. So, on these two cases generally we used to go for grillage foundation. So, first I will show why, means what type of, means how it looks like, what are the forces are coming into picture, what are the design procedures for designing a grillage foundation, then an workout example, right. After finishing this, remaining time, depending on the rest of the time, we will go through the example which we have discussed earlier on gusset base, right. So, grillage footing may be provided, means when we provide, that I have written here what I was telling, that is the loads on the columns when it is extremely heavy. In case of tall building, the base plate required in such cases may be very large dimension and it may not be feasible, right. So, it may not be feasible because the dimension of the base plate required is so high, so large, that it may not be feasible. Another thing is, if the bearing capacity of the soil on which the concrete block is to be provided is very poor, right, if bearing capacity is poor, as a result large dimension of concrete pedestal is also required. So, in that case also we need for grillage foundation. The column in such cases is placed over the base plate, which in turn is supported over two or more tiers of beam, and the whole thing is to be encased in concrete. When I will go through one diagram, then I will be able to inform you how it looks, right. As per IS 800/1962, the following conditions must be fulfilled. Let us see what are the conditions we have to fulfill while going for the release footing. First is, the beam should be unpainted and solidly encased in concrete with 10 mm aggregate and a working cube strength of not less than 15 Newton per millimeter square in 28 days. That means at least M15 grade of concrete has to be provided. These are never painted, as painted beams do not bond with concrete effectively. So, why we are not going for painting, that we understood now, that as the bonding between concrete and steel will not happen properly. So, we are not going to paint it, right. Next is, the beam in each tier are spaced such that the minimum spacing between the flanges of two consecutive beams is not less than 75 millimeter. So, the minimum spacing between the flanges of two consecutive beam will be at least 75 mm. Pipe separators are provided to maintain proper spacing between beams. This is done to place and compact the concrete properly. So, to compact the concrete properly, this has been this used to be done. Next, a concrete cover of minimum 100 mm is provided all around the beam tier arrangement. Concrete cover of 100 mm we used to provide all around the beam tier arrangement, and the size of the base plate is independent of the bearing capacity of the concrete block, since it is to rest directly on the upper tier of the beam, right. Now, the assumptions whatever we are considering for designing the glaze foundation is that the load from the column is uniformly distributed over the base plate. This is one assumption. Each tier of beams distributes the load uniformly to the lower tier, and intensity of the bearing pressure is uniform. These are the three assumptions based on which we are going to analyze and design the glaze foundation, right. Now, first let me show how it look like, this glaze foundation. First, if I see the side view, so this is one beam, right. This beam is provided, and on that again we are providing another beam. In fact, it may be 2 tier, 3 tier, or more than that also may be happen. Right. Now, again this is the plate which is resting on the beam, then the column is there. Here the force is acting, right, and this is the concrete, say okay. Right, this is side view. If I see from the side, and top view will be something like this. So, this will be in this direction. Let us make continuous. Now, say So this is the column from which the load is coming. Right. Now the two tire, here we are showing the two tire beams are placed. So say this will be if we see something like this, then right, these are beams are placed, right. Right, this is top view, column, this is bottom tire, this is top tire, this is base plate, right, this is column. So this is how it looks. This is called grillage footing. Okay. So in this way it has been arranged. Now depending on the soil condition and depending on the load, this number of this tire, beam tire may increase. It may not be 2 tire, it may be 3 tire or more, right. It depends on the magnitude of the load and the type of soil on which it is placed. How the load, basically the load is going to distribute from column to the soil. So how smoothly it can be distributed, that depends how we are going to design it, right. Now before going to analyze, let me show the shear force diagram and bending moment diagram of the means footing, how it is coming, right. Say as we know, say suppose load is coming say P, then if this is resting on the base plate, then what will happen, and then it is going say up to the beam. So when we are going to design this beam, we have to know how much load is coming on this beam and how it is, means where the maximum bending moment and shear force is going to occur. Say if this is P force and area of base plate is A, then the load whatever will be coming here, means in these places, right, this will become P by A, and the load from the beam will be uniformly distributed as per the assumption, because we are assuming that intensity of bearing pressure is uniform. So this will become again the load by total area. This base plate dimension, if we consider, say this is A and the beam length is, let us consider, say L, right. Now if we see the shear force diagram, let us first draw, then what will happen, the shear force diagram will be something like this, right. Okay, this will be the shear force diagram, and bending moment diagram will be, this will be something like this, right. So this will be bending moment diagram. Now what will be the maximum shear force that will develop here and here, as per the shear force diagram, because this is the uniformly load. We can consider that some support is here, right. So, if we see, this will become P by L, this is the uniformly distributed load, into L minus A by 2, because P by A is the intensity of the pressure into L minus A by 2. This will become how much? This will become L minus A by 2, because total is L and this is A. So, L minus A by 2, right. So, this will be becoming finally P by 2 into 1 minus A by L, right. So, maximum shear force is coming this, and maximum bending moment also we can find out, that will become half into P by L into L by 2 whole square, because this is L by 2, right. Then minus half into P by A into A by 2 whole square, right, because of this reaction force, right. So, if we make this, what we will get? Finally, we will find out P by 8 into L minus A, P by 8 into L minus A. So, maximum bending moment M we are going to get P by 8 into L minus A, right. So, these are the design forces which is developing under the load P. Okay. So, with this we can calculate the other things and we can find out the design criteria for the beam, right. So, what we will do now? So, if let us, whatever I was doing, let us see that if P is the load on the column and A and B is the length and width of the base plate, and capital L and capital B is the length of upper tier beam and length of lower tier beams, then first we can find out the load per unit length of beam will become P by L, right. Load per unit length of beam will become P by L. So, maximum shear force will become V is equal to P by L into L minus A by 2, right, because P by L is the usual load into L minus A by 2 at that position. So, this is becoming P by 2 into L minus A by L. Similarly, on the lower tier it will become P by 2 into B minus B by B, P by 2 into B minus B by B, right. So, this is one thing. Another thing is the maximum bending moment. Maximum bending moment in the center will become P by 8 into L minus A. That also I have shown here how it is coming, right, P by 8 into L minus A. So, maximum bending moment on upper tier we can find out as P by 8 into L minus A. Similarly, on the other direction P by 8 into B minus B for lower tier, right. So, these are the forces we have. Now, we will go for the design process. In fact, IS 800 1962 has given some design process, some design criteria they have cited. Like as per IS 800 1962, the allowable bending stress in grillage beams encased in concrete may be increased by 33.33% from that specified in the code. See, allowable bending stress in grillage beam encased in concrete may be increased 33.33%, means we can increase 33.33% from that specified in the code. This is one thing. So, what we will do, that compute the design load by adding 10% of the column load to account for the dead load of the column and grillage. So, when we will go for the design, so first what we will do, that compute the design load by adding 10% of the column load to account for dead load of the column and grillage. So, whatever load is coming, we will add 10% more due to the self weight of grillage and the plate, etc. Then in next step what we will do, compute the required area of the grillage footing from the bearing pressure on concrete. We know the bearing pressure of concrete. So, from that we can find out the area of the grillage footing. Provide a square or rectangular footing as case may be for the base plate, right, as case may be for the base plate. So, either square or rectangular, whatever required as per the base plate will provide. Calculate the maximum bending moment for upper tier beams, right. Now, we will calculate the maximum bending moment for upper tier beams. How much? That is P by 8 into L minus A. The allowable bending stress as per IS specification will be 1.33 into 165, right, for FY 250, because allowable bending stress we know 165, and as per the Coral provision we will increase 33%, right. So, we will calculate maximum bending moment and we will see whether it is below the bending stress or not, or assuming this we can find out the section modulus, right. So, compute the section modulus and select the number of beams to be provided in the upper tier, right. Choose the section from IS handbook. So, what will do? So, as we know the maximum bending moment, we know the permissible bending stress. So, we can find out the required section modulus Z. Z is equal to M by sigma B, right, and then we can find out a suitable section from the IS handbook and then number of section, means number of beam which will be required, right. So, in this way you can make. Now, calculate the maximum shear force per each tier. Calculate the maximum shear force per each tier. That also we know the formula was that P by 2 into L minus A by L. For n number of tiers it will be becoming by n, right. So, maximum shear force per each tier will become how much? V by n. So, P by 2n into L minus A by L, right, if n is equal to number of beams for upper tier. Next, what will do? Check the beam section for shear and crippling. Here chances of crippling will be there, right, because of concentrated load. So, we will check the beam section for shear and crippling, and according to IS code we know that sigma p calculated, that will become this formula as per the Coral provision. In case of beam also we have seen that will become P by n into A plus 2 root 3 H2 into T. Sigma p cal will be equal to P by n into A plus 2 root 3 H2 into T, and this should be less than 1.33 into that sigma b, right. Now, A is the length of base plate, right. Then what will do? We will calculate maximum bending moment for lower tier in a similar way. Maximum bending moment for lower tier, that is in B, P, B minus B by B, right. So, then compute the section modulus and select the number of beams to be provided in the lower tier. Choose the section from IS handbook. So, in a similar way for lower tier also we will do. For upper tier whatever we have done, in same way we will do for lower tier, right, and we will calculate the maximum shear force per each tier. That will be again V is equal to P by 2n into B minus B by B as per the formula, right. So, we can find out the maximum shear force per each tier, that will be P by 2n into B minus B by B, where n is equal to number of beams per lower tier. Then check the beam section for shear and crippling. So, same thing. So, this 7, 8, 9, 10 will be the repetition, means similar way whatever we have done for upper tier we will be doing for lower tier also, same thing, right. So, in this way we will perform. Okay. Now, let us go through one example through which we will be able to understand how we are going to design the grillage foundation, right. So, design a grillage foundation for a compound column consisting of ISHB 350 at 72.4 kg per meter with flange plate of say 350 mm by 200 mm on each flange and carrying a load of 2900 kilonewton, right. The base plate has a size of 750 by 850 mm. The grillage is supported on soil having bearing capacity of 180 kilonewton per meter square. So, these are the things you see, load we have kept same, only bearing capacity we have changed just to see, and in fact load will be very high, then only grillage footing we used to make, but still we are doing with taking same example, almost same example with just little less value of bearing capacity of soil we have taken, right. So, base plate size here we have fixed that 750 by 850, okay, and load is carrying by 2900, here P is 2900 kilonewton, and section column section we are taking ISHB 350, right, okay, and bearing pressure in soil is 180 kilonewton per meter square, okay. So, we will solve this problem by step, steps already we have discussed. So, following those steps, let us try to solve the same problem. So, in step 1 we know that the total load is given, that is 2900 kilonewton, and we will assume the weight of the foundation, that 10% of the total load. So, assuming that, we will get the total weight of foundation as 1.1 into 2900, means 1.1 P, because 10% we are additionally taking. So, 1 into 2900 kilonewton is becoming 3190 kilonewton, right. So, total weight is becoming 3190 kilonewton, and in step 2 we will find out the net area of the foundation base, and that will become A is equal to 3190 by 180. So, this is becoming 17.72 square meter, right, 17.72 square meter. So, length of each side will become L is equal to, if we are providing square size, then this will become 4.21 meter, square root of 17.72, that is becoming 4.21 meter. So, say we are providing overall dimension as, in place of 4.1 let us provide 4.5 by 4.5 meter, right. So, size of the foundation base we are going to get as this 4.5 by 4.5 meter. So, foundation base we got. Now, we will find out the base, means top tier details of the top tier. So, as the width of the base plate was given 850, right, it was given 850 mm, 850 and 750. So, if we take the width of base plate as 850 and length of the tire as 4.2 meter, then maximum moment we can find out P by 8 into L minus L, right. So, this will become 2900 by 8 into 4.2 minus 0.85. So, maximum moment is becoming this one, 1214.4 kilonewton meter. So, maximum moment we are going to get as this 1214.4 kilonewton meter. Next, what we will do? Allowable bending stress. Allowable bending stress, as we know, that will be 33% more than the actual allowable bending stress. Allowable bending stress for FY 250 is 0.66 FY, and 0.66 FY means 165 MPa. So, allowable bending stress is becoming 1.33 into 165 MPa. So, Z required, the section modulus required will become m by sigma b, right. M we got from here 1214.4 kilonewton meter. So, from that we can find out 1214.4 into 10 to the 6 by 1.33 into 165. 10 to the 6 we are multiplying because to convert in from kilonewton meter to Newton millimeter, from kilonewton meter to Newton millimeter. So, after calculating this, the section modulus we are getting as 5533.8 into 10 cube millimeter cube, right. 5533.8 into 10 cube millimeter cube, right. So, if we assume 3 beams, then the Z for each beam will become Z by 3, right. If we let assume that 3 beams are provided in the first tier, that means in the upper tier. So, the Z for each beam will be required this much, right. And from the IS handbook, that SP6, we can find out an appropriate section of the ISMB, that is ISMB 550 we can use, because Z we are getting this. So, closer to that we can consider the ISMB 550. So, if we use ISMB 550, then Z will become 2359.8. You see, whereas we require 1844.6, we are providing little higher side 2359.8 into 10 cube millimeter cube. And for ISMB we know H is 550 millimeter and thickness of the wave is 11.2 millimeter. All these things we can find out from the SP6 from table, right. Width of the flange BF we are going to get 190 millimeter and H2 we are going to get 41.25 millimeter, right. And width of the plate was given 750, right. So, the clear spacing between the flanges of the top beams after accommodating 3 beams will become how much? That is half into 750 minus 3 into 190, that is 90, right. Because BF is 190, you see, like this 3 beams we are going to provide, right. So, this is total 750, this total 750. So, 750 minus 3 into 190, right, 750 minus 3 into 190. So, remaining width will be 750 minus 3 into 190 by 2, means if base plate, means if the plate is provided exactly from here, then this will be the situation, and in that case the spacing will be 90, which is greater than 75. As per the codal provision, we have told already that minimum spacing between 2 beam for using tier will be 75 millimeter, right. So, here it is becoming 90 mm, so it is okay, because minimum is 75 mm, right. So, we can say that the arrangement whatever we are making is okay from the codal point of view. So, in next we will go to step 5, where the beam has to check for the shear, right. Now, maximum shear force as per the equation we know the shear force can be find out from this formula, P by 2 into L minus L by L into N, right. 3 number of beams are there. So, maximum shear we can find out, P was 2900, L is 4.2 meter we calculated, and 0.85 meter is the plate dimension. So, we can calculate by this as 385.51, maximum shear force per beam will become 385.51, right. Now, we will go to step 6, where check for wave crippling, right. For wave crippling what we will do? We will check this formula, we know sigma p cal, that will be P by n into L plus 2 root 3h into TW. So 2900 into 10 cube by 3 into L is 850 plus 2 root 3 into h was 41.25, that was given earlier. This 41.25 we found earlier into 11.2, that is TW, thickness of the wave, right. So from this we are going to get the value as 86.93 MPa, which is less than 250 MPa. That means from crippling point of view, wave crippling point of view, this is also okay. So the section whatever we are going to choose is quite okay, right. So now the shear stress also we have to check. The average shear stress we know V by TWD. As we know, the shear stress is taken care by the wave of the beam. So V was 385.51 as we calculated, and TW is the thickness of the wave, and D is the depth of wave, right. So if we calculate, in fact this is the total depth, this is the means h equal to 550, right. So this is becoming 62.58 MPa, which is less than 133 MPa, because this will be also 33% more than the actual was 100. So 133 MPa, it should be less than 133 MPa. So this is also okay. Now we will go for check for buckling. As we know, clear depth of wave H1, that will be 467.5. So lambda we can find out d1 by tw into root 3 as per the formula from IS code. We know lambda will be d1 by tw into root 3. So d1 is 467.5 by tw 1.2 into root 3. So we are going to get 72.3. 1.2 means tw will become 12, because millimeter I am making, right. So 72.3. So from IS 800 we will get for lambda 72.3, sigma SC value we will get as 109.5 MPa. So the sigma SC allowable compressive stress we are going to get 109.5 MPa for lambda equal to 72.3 and Fy equal to 250, right. So in this way we can find out the sigma SC value, right. Now allowable load from the plate will become sigma SC into Tw into B, sigma SC into Tw into B. Now B will become how much? L plus H by 2, right. L was 850 and H was 550. So 850 plus 550 by 2, which is becoming 1125, 1125 millimeter. So B is becoming 1125 millimeter. So allowable load we can now find out, that is 109.5 into 11.2 into 1125. So this is becoming 1379.7 kilonewton, right. So allowable load we are going to get 109.5 into 11.2 as TW into B is 1125. So this is becoming, in fact by 1000 if I make, this will become 1379.7 kilonewton. Here one thing we did mistake here, that this will be 11.2, because TW is 11.2 not 12, right. So please correct it, that lambda is equal to d1 by tw into root 3, that will be 467.5 by 11.2. So that will become 72.5. However, the in between calculation may have some mistakes, so you please check at your own, right. I am just going through the process through which you can do at your own also. Now actual load per beam will become 2900 by 3. So this is the actual load. So the beams are safe, because allowable load on beam is 1379.7 kilonewton and actual load is coming to beam is 966.6 kilonewton, right. So the beam is safe, right. Now in step 7 what we will do? Same thing we will do for the bottom tire, design of bottom tire. So in case of bottom tire what we will do? As we know, width is 4.2 meter, right, and in fact width we are going to consider not 4.5, 4.2 meter by 4.2 meter, right. Let us consider this one, okay, because calculation I have done in this way. However, if you consider 4.5 meter, then you have to calculate the value accordingly, and you will see that it should be also safe, right. And this B, the width of the plate is 750 millimeter, 0.75. So I can find out the value, right. This will be B minus B for bottom tire, right. Bottom tire it will be P by 8 into P minus B. So P is 2900 by 8 into B is 4.2 and small b is 0.75, right. So maximum moment is going to develop this one 1250.6 kilonewton meter. So in step 8 what we will do? We will find out the required section modulus. Required section modulus will become m by sigma b. M is 1250.6 kilonewton meter. So that we are going to provide 10 to the 6 has been multiplied to make it Newton millimeter, and by 1.33 into 165 as per the codal provision 33% extra we have to increase for the permissible stress. So the required jet will become 5698.8 into 10 cube millimeter cube, 5698.8 into 10 cube millimeter cube, right. Then what we will do? Now if we assume a flange width of 150 mm, then we have NBF plus n minus 1 into 75 is equal to this. So from this I can find out n is equal to 18.55, right. Number of beams we can find out in this way. So if we provide say 18 beams in bottom tire, we can provide, right. So providing 18 beams in bottom tire, how do we find out 18 beams? I hope you have understood that as BF we are assuming as 150. So from this equation means it has to be total 4100. So from this I can find out the number. Now providing 18 beams, the jet for each beam will be required, total jet by n, that is 5698.8 into 10 cube by 18 is equal to 316.6 into 10 cube, right. So for this jet corresponding section we can find out say ISLB 250 at 27.9 kg per meter. So we can try with ISLB 250 at 27.9 kg per meter, right. So Z is given 297, we need Z is 316, right, Z required, and here almost similar way we are given 297, very close to that. H is 250, TW is 6.1 millimeter. These are given in the code for that particular jet, right. BF is 125 millimeter and H2 is 23.7 millimeter. So allowable clear space will become how much? 4100 minus 18 into 125 by 18 minus 1, that is 108. So spacing is given 108.8, which is greater than 75 millimeter. As per the codal provision it should be greater than 75 millimeter. So this is okay. From spacing point of view, the number of beam whatever we have chosen for lower tire is completely okay, right. Now in step 9 what we will do? We will check for the shear force. First we will find out the maximum shear force, right. We know from the formula that maximum shear force will become P into L minus L by 2L into N for n number of beam. So if we put the value P as 2900 into 4.2 minus 0.85 by 2 into 4.2 into 18, so 64.25 kilonewton, right. So maximum shear force per beam we are going to get as 64.25 kilonewton, right. So maximum shear force we are getting. Now what we will do? Now we will go for check for shear. Now average shear stress will become tau is equal to V by TW into D. So V was given, V we have calculated from here, that is 64.25 kilonewton. So 64.25 kilonewton, that is 64.25 into 10 cube Newton, by 6.1 is TW and D is 250, right. So after calculating this, we are going to get as 42.13 MPa, which is less than 133 MPa, right, which is less than 133 MPa. Hence we can say this is okay. So from shear stress point of view, the beam whatever we have considered, the number of beam and the size of beam is quite okay, right. Now it is noted that wave crippling is not a problem in the lower tier beam, because the shear force and all the things are going to distribute. So it will be very less. The concentrated force coming to the lower tier beam is very less. That is why we do not need to check. If the upper tier is okay, then lower tier will be automatically okay, right. So we can use 3 ISMB 550 at 103.7 kg per meter in the upper tier and 18 ISLB 250 at 27.9 kg per meter in the lower tier, and also providing pipe separator with 12 mm phi passing through them at the center and near the ends of each tier of beams, right. So beam, what beam we are going to provide? 3 number of ISMB 550 for upper tier, 3 numbers of ISMB 550, and for lower tier 18 number of ISLB 250, and we are providing some pipe separator of 12 mm diameter just to keep their spacing in a fixed distance, right. So in this way you can design. Now design picture means, if we see, this will be something like this, right. So here we will see that we are providing here the upper tier 3 numbers of 550 ISMB 550, and the lower tier beam we have provided ISLB, how much we have provided? ISLB 250. Here we are providing 3 numbers and here we are providing 18 numbers, right. And what else we know? We have calculated the base plate size, right. That base plate where we have calculated, say we calculate the base plate. So width of plate 750, right, 850. Let the width of base plate is 850 and length of top tier is 4.2 meter, right. So this is what we found, right. Just I am recalling. So overall dimension is, actually this will be 4.2 by 4.2, actually we are going to consider, right, and we saw that this is okay also, right, 4.2. Now base plate is width is 850, right. So we can go with, so this will be 850, right, okay. and other like connections etc. will be standard connection we have to do, that we know, right. So, in this way we can find out the details of the glaze foundation. This also we can find out, it was given, I do not remember, from the calculation I think you can find out, right. Yeah, 4.5 meter, that means 500 millimeter, right. So, this length also we know. Okay. So, in this way you can find out. Now, the remaining part of the previous lecture I like to complete as we have time. Remaining part means, in last day we have discussed about the design procedure of the gasset base. So, the example whatever we have discussed is in last lecture we will solve now, right. So, before going to solve, just by 1 minute I will just refresh the steps, because unless we remember the steps we may not be able to find out properly, means we may be in trouble to go step by step. Just to refresh, just I am reiterating, that is, first step what we will do, that calculate load carried by the column, and we will assume allowable compressive stress in concrete as per the concrete specification. Then area of base plate we will find out, that is axial load by allowable compressive stress in step 2. Step 3 we will find out the size of gasset materials, and that will be assumed according to the some codal provisions, that like the assumed thickness of gasset plate should not be less than 16 mm. This is one. The gasset angle is chosen so as to accommodate 2 rows of rivets in the vertical leg and 1 row of rivets in the horizontal leg, and we generally use unequal angle. The length of gasset material is normally kept equal to the length of base plate parallel to the flange of the column. Then the dimensions of the base plate parallel to the wave can be calculated from this, that is depth of the section plus 2 into thickness of plate plus length of angle plus overhang, right. Overhang should be approximately 1 centimeter from the gasset angle, and the dimension of parallel to flange B will become A by L. A is the total means area, right, and the intensity developed means the intensity of developed compressive stress W can be written as P by BL, P by BL, and in step 5 we can find out the value of minimum thickness required at the critical section. At the critical section, as we know, we can find out this value as A into square root of 3W by sigma Bs, right. Now, if T dash is the thickness of the base plate and T is the thickness at the critical section, which is thickness of base plate plus thickness of angle, then T dash will become T minus thickness of angle. So, in this way we can find out the thickness of base plate, right. Then the connections are designed, right. Then and these connections are designed in basis of that 50% of the forces will be transmitted directly to column and 50% through the fasteners if they are faced for complete bearing, otherwise whole, right. And we can find out the rivet value for a particular diameter of rivet and plate thickness. Then we can find out the number of rivet on the basis of force on fasteners and rivet value, right. So, these are the steps, and rivets will be provided to connect the gasset plate with the column plate. The height of the gasset plate depends upon the number of rivets. The same number of rivets are provided to connect the gasset plate with the gasset angle, and to keep the column in position, nominal size of rivets are provided on the horizontal gasset plate, right. These are the things, and we have seen the example that load was 2900 kilonewton and M15 grade of concrete was used, bearing pressure of 4100 kilonewton per meter square, and ISHB 350 was used. So, let us see, right. So, for ISHB 350 we know H is 350 and B is 250. Now axial load was given this, so area we can find out P by A. So P is 2900, sorry, area we will find out, so P by sigma, and sigma is 4100, so 0.841 meter square, right. Now let use 16 mm gusset plate and ISA 150 by 115 by 15 as the gusset angle on each of the column face. So this we are going to assume. So from this we can find out the minimum width of the base plate. Minimum width of the base plate will be what? The 350 which we got earlier, this H, because this will be the 350, right. So 350 plus 2 into 16 plus 2 into 115, this is the angle, right. So 612. Now let us provide say 630 millimeter base plate width, right. So projection of the base plate beyond the gusset angles will become how much? 630 was total minus 612 was actual, so 630 minus 612 by 2 is equal to 9 mm, and as per IS code minimum overhang should be 10 mm. So we are providing say 10 mm, right. So let us increase from 630 to 640 mm base plate width. Okay, we have used earlier 630, now we are going to use 640, because to make minimum overhang more than or equal to 10 mm. So if we make 640, we are going to get overhang as 640 minus 612 by 2, that is 14 mm, right. So overhang we are getting 14 mm, which is greater than 10 mm. Now length of base plate will become this 841 into 10 cube by 640, right. 841 was the total, means area by length, 841 into 10 cube is the total area. So area by length is equal to, sorry, width is equal to length, so 14 millimeter. So let us use 1350. Okay, so the pressure whatever it is coming into load intensity, that is 2900 by length into width, 1350 into 640, P by L into B, that is becoming 3.36 MPa, which is less than 4.1, because in the example, in the question it was given that allowable pressure was 4100 kilonewton per meter square or 4.1 Newton per millimeter square, right. So this is the developed one, 3.36 is less than 4.1, so it is okay, right. So now we will go for the dimension whatever we have arrived, that is 640 by 1350. Okay. So in this way we are choosing the dimension 640 by 1350 millimeter, right. Now in step 6 what will do? Length of the base plate acting as cantilever, that C value will be getting 115 minus 15 plus 14, 14 was the overhang, right. 115 plus 14 minus 15, so 114, right. So now we can find out T is equal to A into square root of 3W by sigma base, this is basically A or C, whatever you can say. So 114 into square root of 3 into W was 3.36 by 185, so this is becoming 26.6 or 27 mm. So thickness is coming 27 mm there, so thickness of the base plate will become 27 minus the angle of the thickness of the angle, so this is 12 mm, right. So 12 mm we are going to get. Now what will do? Now let us provide 16 mm thick base plate, means in place of 12 mm little we are increasing, as it should not be thinner than the gusset plate. In coder provision it is told that it should not be thinner than the gusset plate. So thickness of the base plate will be minimum 16. So, the finally we are deciding the dimension of the base plate as like this, that is 1200 by 1640 by 16, not 1200, sorry, 1350 by 640 by 16, 1350 by 1350 we got, right, we got 1350 here. So, 1350 by 640 by 16, right. So, in this way base plate dimension has been fixed. Now, let us go to the connections. Let us provide 24 mm power driven shop rivet, right. So, the gross diameter will become 24 plus 1.5, that is 25.5 millimeter, and strength of rivet in single shear will become, as we know, tau VF into pi by 4 into d square. So, 51.0, and strength in bearing, that is sigma PF into d into T. So, finally, we are getting rivet value as 51.07 kilonewton. Now, let us assume that the column ends and gusset materials are faced for complete bearing. If it is faced for complete bearing, then we can find out that 50% is going to taken by that. So, P by 2 into this RV, so 28.4, and in two phase. So, let us provide say 32 numbers of rivet to make it symmetry. If rivets are provided in 2 rows, minimum pitch S will become 2.5 into 5, that is 2.5 into this, that is 63.75, that is 65 millimeter. Now, let us provide edge distance of 1.5 pi, that is 1.5 into 25.5, so that is becoming 40. So, height of gusset plate can be found, angle length, that is 150 plus 2 into 40 plus 65, right, 65 is the minimum pitch. So, 295. So, let us provide 300. So, height of gusset plate is also decided. Now, length of gusset plate is equal to length of base plate, that is 1350 millimeter. So, let us provide a gusset plate size of 1350 by 300 by 16 mm. Okay. So, in this way we can find out the gusset plate size. So, providing rivets a horizontal distance of 80 mm and edge distance of 200 mm, and for vertical arrangement a vertical distance of 80 mm and edge distance of 50 mm. So, in this way we can provide. So, because of shortage of time, I am not going to discuss much. So, I hope you will be able to calculate the details in proper way, right. So, with this I like to conclude today's lecture as well as the last lecture, means this is the last lecture which I supposed to deliver. So, thank you very much for your attention. I hope with this you will be able to get some idea about design of steel structure, and further if you have any confusion, please let us know so that we can clear it. In fact, certain mistakes you may find out in my lecture, and you people, mean those who are viewing this video lecture, are the right person to review. So, if you find any mistakes, kindly let us know so that we can overcome those mistakes and we can modify the things. Because of shortage of time, we have done very hurriedly. So, let us know if we have done some mistakes in calculation of the workout examples, etc., so that we can modify it. So, thank you very much for your patience to listen all the lectures of design of steel structure. Thank you.